So this is the revision seminar for AQMF on integration. And as with all of them, I can't guarantee that I'll cover everything, but please ask questions if there's anything that I've missed or anything that you don't understand. Cool. Okay. So I'm not going to go through the whole everything in integration, and I'm going to do the upper and lower sums thing later. That'll come later. I'll be in a separate video for those who are watching on video. I want to talk about, in particular, the techniques of finding an integral for something, the substitution and integration by parts, and how to decide which one you're going to do in any given situation, and just areas under curves, and as much as I can to go with this, but in particular they're the ones I really want to talk about. So first let's start. The purpose of an integral is to find an area under some sort of curve. So the purpose is finding areas. So the concept is you've got something like that, and you want to find an area like that. That's the idea of an integral. So if this thing was fx, and this was a, and this was b, then that area there would be the integral from a to b of f of x dx. It's always good to have that sort of picture in your head. Except it's worth pointing out that if your function goes below the x-axis, or t-axis, or whatever it is, then if you do an integral from, say, here to here, then that part will count as a negative area, and these ones will be positive. Okay, so if the area is above the x-axis, it will count as a plus. And if the area is below, it will count as a negative. So from ordinary everyday thinking, areas can't be negative. That doesn't make any sense, but that's how the formula for the integral works. Which means that if you are specifically asked to find the area, then you need to find this bit separately, because it'll come out as a minus, and you'll need to turn it into a plus and add it on instead. So I'll get to that. But still the same, all of this area together, counting those two as plus and that one as minus, will be the integral from a to b of f of x dx. Okay, so the answer for that integral will be this minus that plus that. That's how it will work. So it is possible for the integral to be 0 if all the negative bits happen to cancel out the positive bits. Right. That's the idea behind it. But the fundamental theorem of calculus says that it doesn't just find areas, it's the opposite of differentiation. That's what the fundamental theorem of calculus says. So the fundamental theorem of calculus says that if you want to find one of these areas, then what you need to do is you need to find something that differentiates to give the function that you have. So if f of x, is a function so that f dash x is little f, then the integral from a to b of little f of x is that, which means that you sub in the b and the a and subtract. That's the fundamental theorem of calculus. The fundamental theorem of calculus says that you can do integration by doing the opposite of differentiation. That's why it's fundamental, because once you start doing that, you don't even realize that you're even using a theorem. Basically what this means, which means that's the fundamental theorem, which means that integration is the opposite of differentiation. Okay, that's what it means. And it's really fundamental, and before Newton and Leibniz had come up with this idea, no one even realized that they were connected, integration and differentiation, because differentiation is for finding slopes and integration is for finding areas, and they don't seem to be very closely related, but in fact they are, which is helpful to us because integration is actually extremely difficult compared to differentiation. And that's because it's differentiation backwards. Okay, so what this here is called is a definite integral. I need to just some terminology in case you're not sure. So a definite integral is something with letters here, with numbers in these spots here, that you actually do the integral and you do the top minus the bottom. That's a definite integral, and the answer will come out to be a number because you're trying to find an answer for an area on the page. So but there is also the indefinite integral. Where we don't put numbers in these spots here. I need to put boxes around them so you can see where one thing ends and the other begins. There's also the indefinite integral, and the answer to that is a function. It's a formula. And what it's supposed to do is it's supposed to cover all possible formulas that could differentiate to give this answer. It's the answer of doing differentiation backwards. But you're supposed to, there's actually multiple functions that would differentiate to give this, and that's why we put the big plus C, because any number in that spot would differentiate to give that answer there. So I'm trying to cover all the possibilities, which I will write down. So with the indefinite, trying to cover all possible functions that could differentiate to give the f of x. Okay? That's the aim, which is why the plus C. Okay? That plus C is saying, well, if I put any number there, C for constant, when I differentiate the plus C, it'll become a 0, because it doesn't involve any x's, and so I'll get back to the same answer. Okay. Awesome. So, I mean, on paper, if you ever ask for an indefinite integral, you know you're wanting a formula, and hopefully you're used to that by now. But that's the idea behind it. Okay, awesome. So when they say using the fundamental theorem of calculus, they just mean integrate it. That's all they mean. So, cool. All right, awesome. So some techniques of finding indefinite integrals, which is the same as techniques of finding definite integrals. So I should say here that back here in the fundamental theorem of calculus, that capital F of x is allowed to be anything that differentiates to give that, so you don't have to include the plus c, because it will work no matter what c is. So here, you don't need the plus c inside that bracket because it'll disappear anyway, because you're going to do this minus that, so you get a plus c and a minus c and they'll cancel out anyway. So you can choose anything as long as it differentiates to give this answer. All right, cool. So let me list for you the techniques of integration that are in your course. In Maths 1A, they learn about 4 other techniques, and they all cry about it. So you're quite lucky, actually. So we have, these are the techniques of trying to find integrals. All right. So, technique 0, because it doesn't really count as a technique. Have I spelt techniques right? Yeah. Yeah, I have. I need to put the U in the wrong spot. There's my dyslexia. I have the tendency to just put random letters that are actually in the word in a random spot. Technique, that's better. Okay, yeah. If there's a word with a Q in it, I have a tendency to write a Q first, no matter where it is. That's my dyslexia. So, techniques of integration. Technique 0, as in it's so basic it's not even a technique, is just do it. Okay? And under this category, we have the power rule, which you should be so familiar to you, meaning that if it's not familiar to you, then please make it familiar by the time you get to your exam. So the rule should be that if you see any power at all, so as an example, integral of 4x cubed dx. Okay, so the rules of integration say that if there's a number multiplied on, it will still be there afterwards. That's one of the basic rules. And then the other basic rule of integration is if you see a power, then your power goes up by 1, and you divide by the new power. Okay? So, under this category is we have the power up by 1 and divide by new power. Okay? And that is the most fundamental of all possible integral techniques. And this works for any power at all, except x to the minus 1. Because if you put the power up by 1, it'll be 0, and you can't divide by 0. Okay? Okay, so the other thing on the just do it is what do I do if it is x to the minus 1? Like that. Well, you want to... And the integral of 1 on x is ln x, and that's what you should... That is something that we need to know. Write it on a cheat sheet or get so familiar with it that you remember. That's the other thing you need to know. And the final thing which you need to know, so we had that the integral of 1 on x dx is ln x. Okay, that's our second law. And the third law is about e to the power of x. Well, when you differentiate e to the x, nothing happens, so it'll be the same if you integrate it. That's basically it. Okay? They are the absolute basics of integration. Basic meaning that they're more simple than everything else you would do, not to say that they're necessarily easy, but that's the way that works. Okay, that's pretty much everything, and most of the things that are in economics are either ln or e to the power of or some sort of power. I think I've covered everything. Let me just see if there's anything else on your list. Yeah. Wow. Okay. All right. And under this category is something else that is worth knowing that your lecturer will probably do without telling you that that's what they're doing. There is one like this. So suppose we had something where we would know what to do if it was just, if I could cover up the 4, if it was just e to the x. If it was just e to the x, I would know what to do, and the integral would be e to the x. So we would like to hope that it's e to the 4x. Okay? But if I differentiated this, I would have to use the chain rule, and I would get e to the 4x times the derivative of that, which would be 4. So there's supposed to be a 4 here, but there's not. So I really need there to be a quarter here. And the rule goes, if the thing that is here, or wherever it is in your function, if the derivative of it is a constant, so if it's like ax plus b, then pretend it's just an x, and then divide by the a. So that's what the rule goes. So this is sort of divide by the constant derivative. Now technically this is actually substitution, but it happens so often in real functions that you might try and actually integrate that it needs to be right at the bottom in technique 0 of something that you should be able to do. So as another example, so if I had root 3x plus 1, that, so far I know that my rules say that anything that's written as a power I can do, so I'll rewrite this as a power. Okay, root is a power of a half. And the rules say, well, I put my power up by 1. So it's at a half, it'll go up to 1.5. And 1.5 is actually 3 halves. And I'll have to divide by that new power. So dividing by a fraction means turning it upside down and multiplying instead. But because the inside has a constant derivative, I can just divide by 3 as well. Or times by a third, if you like. Oops, sorry about that. So the 2 times 1 is 2, and the 3 times 3 is 9. That's how I got my 2/9. So that's another example of the same thing. I don't know if they teach that to you in your course, but maths lecturers have the tendency to do it without telling you that that's what they're doing. So this works for all possible things, even ln. Well, the integral of ln we don't know how to do. But there's another example, which would be sort of that. If it was 1 on x, then the integral should be ln, right? Okay, so if it was 1 on x, the integral would be ln x, but it's actually 3 minus x, and the derivative of that is a constant, and that constant derivative is minus 1. Because the 3 will disappear, and that will be minus 1. So it's minus ln. So that rule, now I should say you can do this by substitution, and I'll do one of these by substitution afterwards so you can see how it works with that. So feel free to always use substitution if you want, but in the interest of making the whole process of integration quicker, it's a worthy thing to learn. Just have a quick check that the thing on the inside, if its derivative is just a number, then you can do this trick. Just do it as you would as if it was just x and divide by the constant derivative. This trick will only work if the derivative of the thing that is here is a number. So if that was 4x squared, couldn't do it. Couldn't divide by 8x. Okay? This will only work if the derivative is a constant. Okay. So that's technique 0. Technique number 1 is rewrite it. Again, your lecturer wouldn't have told you to do this either, because they would have expected you to just figure it out. But as an example, let me there's that integral there. So all of these techniques are designed to turn an integral that you don't currently know how to do into one that you do. So you want to turn, we're at technique number 1, you want to turn this back into something that is at technique 0, something that you can just do. So if I expand these brackets, it'll become x cubed, x squared times x is x cubed, and x squared times 1 is x squared. It'll become this. And I can integrate both of those. So remember that if there's a plus, you can just do them separately. So the integral of this bit, the power goes up by 1, and I divide by the new power. the power goes up by 1 and I divide by the new power. And that's the integral. So if you do see something, the first thing you should think of, if you do see something that's just not on the list of things that you know how to do already, the first thing to think of is to try and rewrite it in a different way. And I already did that for a previous question. You might see that. That's actually on my screen. Oh, it's not on yours. I've got a big hole in my screen. Oh well. You can rewrite this as well, because that dividing by root x is just x to the minus a half, isn't it? So that's the same as x plus 1 times x to the minus a half. Okay, that has become that. The minus is because it's on the bottom of the fraction. And now I can expand the brackets again. X to the 1 times x to the minus a half would be x to the half, because you add the powers. That's a 2. And 1 times x to the minus a half is that. So now I've expanded the brackets. And now I can go, well, I can integrate them now because they're just powers. Half plus 1 would be 1.5, so that's 3 over 2, and I have to divide by that new power. So times by the upside down. Minus a half plus 1 gets me up to plus a half, and I have to divide by a half, which is the same as timesing by 2 over 1. So I've got 2/3 of x to the 3 halves plus 2x to the half. And it's fine to leave them as powers, even if the original one had square root, it's okay to leave them as x to the half. So all of this is actually just under the category of rewriting it. We look at that and say, okay, root x, I can rewrite that as x to the power of a half. It's on the bottom, it can be minus a half. And then I can expand it out. So that's the first thing to think of, to say, when I look at this, is there a way of me rewriting it so that I can just use that power rule, or the 1 on x, or the e to the x thing? Okay, awesome. Doing really well. Cool. So that's technique number 1. Technique number 2 is substitution. So far on our list we have just doing it, which is using that power rule, power up by 1, divide by new power, or the e to the x, or 1 on x, or possibly dividing by the constant derivative. The second one is rewriting it so that it looks like those things, even though it didn't previously. And the third one is to use substitution. So once you've looked at it and went, if I can fiddle with that all I like, I still won't be able to do anything, that's where substitution comes in. Okay? So the purpose of substitution is to deal with things where there's something inside another function. Okay? So it's for specifically dealing with formulas inside other functions. So that's what, with differentiation, that's what the chain rule is for. So it's sort of like the chain rule in reverse. So the chain rule was for dealing with that situation as well. If I saw e to the x squared and I differentiated it, I would differentiate it if it was just an x and then multiply by the derivative. Now that's really easy. Chain rule is easy compared to substitution because we're trying to do it backwards. Okay? So the purpose is to do the chain rule backwards, so it's for the same situation. It's easier to describe with an example. So what if we have that? So my advice for doing substitution, knowing when to do it is when there's something inside another function. I know what e to the x is and how to cope with that, but I've got x squared inside it instead. So that's telling me that substitution is probably the thing I need to do. Okay? So, right, this is how I do substitution. I have no clue what your lecturer did, but this is what I do. If it is different to your lecturer and that freaks you out, I apologise, but it's the way that I find the most easy. I think it's the same, because I did have a quick look at some of the lecture notes. But your lecturer will not care if it is slightly different to what they do. Oh, that's actually page 4. Just organising the notes. Okay, so what you do is you imagine that if I did have e to the x squared and I differentiated it, the chain rule would mean that the derivative of this would have to be multiplied on. And so you need to look to see if the derivative is there. And the derivative of x squared is 2x, so it's almost there. There's just the numbers wrong. I've got 1x instead of 2x. So 2 pieces of advice are find the most annoying bit that's inside something else, and then also check to see if the derivative is there. Even if it's not, it's still worth trying. I will write those down in a second. But this thing here is inside the e to the power of, so I'm going to call it u. Because what I'm about to do is I'm about to rewrite this all in terms of a different variable. I'm going to rewrite it in terms of u instead of x, and I'll do that integral instead. Okay? And all this does is turn it into another integral that we hopefully know how to do. You can actually think about it as saying, well, this x e to the x squared is a formula of some sort, is a graph of some sort, and I'm actually going to draw that picture. This is not what e to the x squared looks like. So you've got your x-axis here, which is marked out like that. And the concept is if you're doing an integral, you want to find an area. Well, when you're doing an integral by substitution, you're actually going to remark the x-axis in terms of u. So if I said that u was equal to x squared, I might need to have a few more markings here. Then when x is 1, u is 1 as well. So that's x equals 1, but that's u equals 1. And when x is 4, u is x squared, so when x is 2, u is actually 4. And when x is 3, u is actually 9. And so in terms of u, my u-axis is all scrunched up. And so it's sort of, then 16. And so these are all, in between this 9 and 16, there's all these, if it was drawing it with a u-axis, like that, I've got 1 here, and there's 3 in here, because that next one is 4, and the next one is 9, and the next one is 16. And so it's all scrunched up at this end. And so what you actually have to do is spread that out again and calculate the area there. So you need some way that says areas on this axis, because they're all scrunched up, are smaller than they appear. So when I spread this out, all spread out neatly, this will get all spread out like that, because that 16 actually really belongs over here, so the whole graph gets stretched out. And if I calculate areas on this, they'll be much bigger than they really are, because the real area is over here, and this has been all stretched out. So I need some way of figuring out how the areas of one relate to the areas of the other. That freaks you out, completely ignore it, but it helps some people. So what I've got here is my u equals x squared, and I need to know how areas in terms of u relate to areas in terms of x, and that means I need to know how u changes when x changes. So that means I need the derivative. So this is telling me that a change in u represents whichever x I'm up to, it's 2x times the matching change in x. So that's saying that changes in u are much bigger than changes in x, which is what this diagram here is saying. A change of 1, not much bigger the other way around, but all the same. A change of 1 here represents a really huge change in u. So if I change 1 in the x, the change in u is actually a lot bigger because it goes from 9 to 16, not from 3 to 4. That's what that means. All right, let's ignore that for a bit and I'll just show you the process now. U is x squared, and I've made that decision because the thing inside the e I wanted to call u. Then I need to deal with the dx, so I need to create a dx by doing a derivative, and I'm going to arrange it like this. And what I'm going to do is I'm going to look to see if this x that is next to my dx is already in my formula. And it is, because you see here is an x and a dx. This is all multiplication here. I'm going to focus on this bit next to the integral, ignore the integral sign for now, and say, look, x and dx are multiplied together in this formula, and here they are again. The problem is I don't have a 2 up here. I don't have a 2 there, so I'm going to get rid of that 2 by dividing both sides of this formula by 2. Half of du is x dx. And now, the x dx must be equal to a half du. So let's rewrite our integral. To be completely clear, I'm going to rearrange it first so that you can see what's going on. I'm going to put the x dx x over here because I can rearrange multiplication in any order. That is u, the x squared. The x dx is a half of du. And so I can replace all the things involving x here and all the things involving x and x dx here with u's and du's. So now I have the integral of half e to the u. So the half being multiplied on will stay there. And the e to the u, well, that's just e to the u again when we integrate, plus c. And the final step is to figure out what u is. Well, it was x squared back here, so that's actually a half of e to the x squared plus c. So let me draw the process. And I'll do another example, of course, because this can only be understood by talking through lots of examples. So the process was, first I decided from here what u had to be. Then I differentiated it and tried to arrange that the expression here that involves dx, I find as much of this to include with the dx as possible and figure out what that is in terms of du. And then I subbed it all in, which is what this step was. I did the integral, and then I put the x's back. That's what I did. So they're all the steps involved. Choose your u. Let me write them down. So step 1 is choose u. It must be inside something else. And then do du on dx. And then rearrange to get sort of something du equals something dx. Sub into the integral until, oh, there's only one L in until all x's are u's. Do the integral. Sub in until all u's are x's. That's how substitution works. Now, it seems like a long process, but to be honest, it's the only way. And it does have the advantage of having a process that you can work through rather than just coming up with the answer. So let me do another example. These examples are here from the assignments. So let me go. All right. So I'll go back to one of these. Okay, so this one's actually 6A from assignment 9. All right. So I need to look and see, I need to find a part of it that's inside something else. And this here is inside the power of 5. So that's a good candidate for U. Okay, that's how I made my chose my U. The next step is to differentiate it so that I can deal with the dx. So far this part has been turned into u to the power of 5. I need to turn the dx into something involving du. So let's see. du on dx is, so we've got 2 will stay there, times by current power, reduced power by 1, 12. Don't forget that you're differentiating here, so don't get your differentiation and integration mixed up, because it will just go badly for you. So we have 8x cubed plus 12, okay? So the du is 8x cubed plus 12 dx. Okay, so it looks like I need to create something that's 8x cubed plus 12 multiplied by dx. We can think of this as being dx on 1 and think of it as a fraction, because remember we're just looking at this bit. We're ignoring that and pretending that the dx is something that we can multiply. And so we have a 2x cubed plus 3 here, a 2x cubed plus 3 dx. We want to make this look as much like that as possible. So dividing by 4 ought to do the trick, because if we divide that by 4 it'll give us the 2, and divide that by 4 it'll give us the 3. So I had to look to see what was actually in my integral and see how I could turn this into what was already there. Awesome. So it looks like we've dealt with everything. The 2x cubed plus 3 dx is going to become a quarter of du, and that is going to become a u there. So we've got so that is a quarter of du, and that is u to the power of 5. I didn't change the 5, so it's still there. And now I need to do that integral. So I need to go back to my other techniques and say, how can I do that? Well, if I rewrote it as u to the minus 5, I would know what to do. So now the quarter is a number being multiplied, so it will stay there. The u to the minus 5, I'll go up by 1, which will take it to minus 4, because that's what you go up from minus 5, and I'll divide by my new power. And so it looks like I get minus a 16th of u, plus c, minus a 16th of u to the minus 4 plus c, which is, now what was u? 2x to the 4 plus 12x. And that's the answer. It's perfectly appropriate to leave it as minus 4. If you were really in a particular frame of mind, you would rewrite that as 1 over that to the power of 4, but it's not actually necessary. So I'd leave it there if I were you. So that's substitution. Okay. So this step here, the hardest part of substitution is figuring out what to do with this to turn it into what you actually have. As far as I can tell from your examples, I don't need to show you anything too much fancier than that, because there are even cleverer ways of dealing with substitution. cleverer in the sense of they are things that, you know, there's always other techniques that you haven't heard of before. I'm going to do one more. So this was this is assignment 10, question 6A as well. So substitution is the first thing you should do before anything else, after looking to see if you can rewrite it. And I can't rewrite this in any reasonable way to make it into something that I know what to do, because ln x times x to the minus 1 is still bad. So the next step is to try and do substitution. So you need to choose something to be u. So if I choose u to be x, that's not going to help because I'm just going to replace all the u's with x's, all the x's with u's, and it'll be the same integral again, just with u instead of x. So I could possibly choose u equals ln x, and that might work. So it's okay to say this might work and give it a go. Okay, so u is equal to ln x. So du on dx is 1 on x, because that's the derivative of ln x. So if I want to separate all the u's and the x's like that. And that's really useful because I actually have a 1 on x dx here. If I rewrite my original integral, if you think about it, that's the same as ln x over 1 times 1 over x. That gives me the same answer. And so that means that the ln x is u, and the 1 on x dx is du, because that's this part here. So that goes there, and that goes there. Well, there. And I know how to integrate u. That's u to the power of 1. So the power will go up to 2, and I'll divide by the new power. And then finally that will give me a half of ln x squared, because u was actually equal to ln x originally, so I can put that back in. So all the steps were done. There was just a very creative spot where I just went, let's just try substitution. I can't really see something inside something else, but I'll just pick something that's annoying and call it u. The ln x was the most annoying bit, because if it wasn't there, I would know how to integrate it. So I'll call that u and hope that it works. Okay? And that's actually a perfectly reasonable approach. All right. There is one more technique that you've been taught, which is integration by parts. So let's see. So what were we up to? Number 3. Okay, so we've already done the chain rule backwards. Well, actually, that's what the aim was. The other thing that you can do in differentiation is the product rule. If you've got two things multiplied together, you can differentiate one and keep the other, and then keep this one and differentiate the other. That's the product rule for differentiation. So we want something that helps us do integration when there's two things multiplied together as well. So this is for two things multiplied together. That's what it's designed for. So if you can rewrite it or look at it as two things multiplied together, then that's what integration by parts is for. You need to be able to integrate one of those parts and differentiate the other. Okay? So you'll be you integrate one and you'll differentiate the other. It's worth pointing out that integration by parts will not do the integral for you. It will just turn it into another integral that you then need to know how to do. Okay? Just like substitution. Substitution just turns the current integral into a new integral that you need to know how to do. And integration by parts is the same. It turns the current integral into a new integral that you also need to know. You need to know how to do after that. It may be that integration by parts will work for that and you'll do it again. It may be that substitution is what you'll need for the new integral. Or it may be that you'll just know how to do the new one. So that is the big thing in your head for integration by parts, is that you need to choose which one to integrate and which one to differentiate based on the new integral being something that you know how to do. Okay? So to choose which is which, So choosing which of these to integrate and which one to differentiate. So rule number one is, if you don't know how to integrate it, then that can't be the one that you integrate. In the sense of you have to know how to integrate it by technique 0, basically. You have to actually have a formula for it. And 2, differentiate the one that will disappear eventually if you differentiate it often enough. That's the other idea. So you want to get the one to differentiate, you want it to go away when you differentiate it. So become a constant, hopefully, or if you do it enough times, it will disappear. So if you've got x, you should almost always differentiate that one, because when you differentiate it, it will become a 1, and 1 times anything is the same. So I'll do some examples so you know what I mean, but they're the big choices. Okay. So the formula for it goes like this, that your lecturer would have told you. Okay, they may have put the dash on the U, it doesn't matter. I'm going to write this again because I have an order that I write this in that helps me remember. So the point is that it starts as two things multiplied together, right? And then you'll still have an integral at the other end, which will still be two things multiplied together. And in the centre you'll still have two things multiplied together, but they won't be an integral anymore. So I know that there's a uv and a uv and a uv, and I know there's an integral at the beginning and an integral at the end, and an equal sign and a minus sign. And then the final step is that one of them has a dash here and the other one has a dash there, so I could just as easily do it this way. Either one of those is integration by parts. Okay? And what we mean by putting a dash on this is to say it's been differentiated. So I actually need to look at it as something that's a function and something that's already been differentiated, so I have to integrate it. So this dash is saying integrate this one. And this one's saying differentiate this one. Okay? So when I integrate the v, it ends up here and here. And when I differentiate the u, it ends up there. So you actually integrate first and then differentiate the other one. So some people are actually able to remember this straight up, where you can say, well, let's just choose the one, and we'll integrate one of them first and leave the other one behind, and then I will keep that integral and differentiate the first one. So it's a little like the product rule, but slightly different. But with the product rule, you differentiate one and keep one, and then you keep one and differentiate the other. With this one, you integrate one and you differentiate the other. Okay. So it makes the most sense with examples, of course. Okay. All right, this is assignment 10, question 4a. And they specifically asked you to use integration by parts. Personally, I would use integration by substitution to do this, because there's something inside something else. But they've specifically asked for integration by parts, so that's what we'll do. Because of course substitution's earlier in the year, so it's number 2. I would always do that before by parts. So I need to choose which one is the u and which one is the v. Okay? So this is going to be, in fact, for me, I just always make the first one u and the other one v. I need to choose which one has the dash, which one is going to get integrated, which one is going to get differentiated. Okay? All right. In fact, I need a bit more space to do that. I'm just going to rub this out. I'm going to leave a gap to do some working. Just let me sort out my pile so that when I photocopy it, it ends up in the right order. Okay. All right. I'm just going to leave a little gap here, and I'm going to start doing my integral again because this is where I want to do some working. So that's going to be u and v, and one of them is going to have a dash. So my choices are, I have to know how to integrate it. And technically I know how to integrate both of these things because this is the divide by the constant derivative rule, and this one's just the ordinary power rule. So that particular version of know how to integrate it doesn't help me. But I need to choose the one to differentiate that's going to go away. And if I differentiate x, it will become a 1, which is going away. I can deal with a constant I can deal with. So I'm going to choose this one to be the one that gets differentiated. So it's this one here that's going to get integrated. So let's see, up here, u is going to be x, and so u dashed is 1, because that's the derivative of x. V dashed is x plus 3 to the 4. Pardon me. And so the integral of v dashed, so the power goes up by 1, and I divide by the new power, but it's not just x, it's x plus 3, but the derivative of that is 1 anyway. So technically I'm going to divide by 1. So just to be absolutely clear, that's my constant derivative of the inside. Cool. So now, using that information, I know that this is going to be u v minus the integral of u dashed v. So u is x, and v is 1/5 of x plus 3 to the 5. U dashed is 1, and v is 1/5 x plus 3 to 5. Okay? And now, as I said, I still have an integral to do. All this did was turn the original integral into a new one that I hopefully know how to do. So this bit, I've got nothing left to do on this. And this bit, well, that 1 times doesn't do anything. So that 5th is being multiplied, so it will stay there. And I'll do the same trick. The derivative is a constant, so I can just power up by 1, divide by new power, and technically divide by the constant derivative. And now that I've finished the last integral, I can do a big plus c at the end. So I get 1/5 of x plus 3 to the 5 minus 1/30 of x plus 3 to the 6. That's how integration by parts works. Okay? So, just like with substitution, once you've actually done the integration by parts, you still have another integral to do afterwards. Okay, so the process of integration by parts only takes you halfway. You still have to finish it off after that. Just a couple of things I want to point out here. When I was doing this, and I fit it all on the screen at once, sort of. Yeah. When I was doing this, for me personally, differentiation is down and integration is up. So you'll notice that I have the dashes on the bottom line for both of them, and I drew this first, and then I figured out that, and I drew this, and I figured out that. That's just my personal little quirk. But it helps me to remember that I have to integrate one and differentiate the other, because otherwise I have the tendency to differentiate both of them. And you're supposed to integrate one. So, yeah. Okay, let me do another example. This is assignment 10, question 6b. So we already did this one by substitution, and that's what you should always do. It's ln x on x. You should always do it by substitution if you can, because substitution is actually easier than integration by parts, and gives you a cleaner answer when you've finished. However, this question specifically asks you to do it with integration by parts. So here we go. So we know, I'm going to leave a gap like I did last time. But even before I do that, I'm going to need to rewrite it as two things multiplied together. So the only way I can think to do that is to do ln x times 1 on x. Awesome. So the u here, so my choice is I need to pick which one I have to integrate now. And I cannot integrate ln x because I don't have a formula for that. I don't have a formula for the integral of ln x, so I can't possibly integrate that one. I have to integrate that one. Cool. So I now know that u is in fact ln x, and therefore u dashed is 1 on x, and v dashed is 1 on x, and so therefore v is ln x, because the integral. Okay, great. So this will come out as uv minus u dashed v. Okay, so the integral, the dash will disappear first, and then a dash will go on to the other one. So let's see, u is in fact equal to ln x, and v is also equal to ln x, and u dashed is 1 on x. This is not looking good, and v is ln x. That's not very nice, is it? That's where I started. But this is actually one of the other techniques. So if I do it in the right way, I know that this is probably too much writing the same thing again, but I need to be clear. So ln x okay, just rewriting what I've got. I started with this, and then it became this. You'll notice that this is the same as what I started with, only over here it's a minus. So if I put it over the other side, there'll be 2 of them over there. So if I add this to both sides, I'll have 2. That's an ln x there. So I put this over there, and now there's 2 of them. And so now I can just divide both sides by 2. And now that I've actually finished, I'll put a great big plus c. Technically, I should have put it here as soon as this side had no integral. It doesn't really matter. I call this method going round in circles. You've gone forward to end up exactly where you started with, and then you can put that integral on the other side. So. To be fair to you, this is probably the only situation you'll see it in this course, because it's much more likely to happen if you've got trigonometry stuff. And you don't really consider trigonometry in economics very often because you don't need to. ln is really an e to the power of the most common things in a financial and economic sense. So this is one of the rare situations. I'm going to do one last example of integration by parts. Okay, this one is not in any of the assignments as far as I'm aware. Okay, so the final example of integration by parts is this one I'm going to do, and the same trick as always, just going to give myself a little space to talk about the U's and V's. Okay. Right. So let's make our decision again. I need to choose which one to integrate. If I integrate the x squared, it will go up to x cubed, roughly, be a third of x cubed. And that is in some sense worse. I know how to integrate both of those things, so my decision needs to be based on something disappearing if I differentiate it. If I differentiate the x squared, it'll become a 2x, and then I could do integration by parts again, and then it would become just a 2. So if I differentiate this often enough, it will go away. And so that's the one I need to differentiate. So I'll put the dash on the other one. So the u is x squared, and the u dashed is 2x, and the v dashed is e to the 2x, and the v is, right, if it was just e to the x, it would be the same, and the constant derivative is 2. So I divided by the constant derivative. You see why I think that needs to be in technique 0? Because when you're doing integration by parts, you keep having to do it all the time. So it needs to be something that you're just familiar with. Okay, so this is going to come out to still u times v, still u times v, but the dash has moved over to the u now. It was on the v before. And now I use my list of what I've got up there to fill everything in. So let's see, u is x squared, v is a half e to the 2x, u dashed is 2x, and v is a half e to the 2x. And there's still a dx here. Let's just do some nice simplifying to make it look pretty. And that 2 and that half will multiply to give 1. And so now we're here. Thing is, we still don't know how to do this integral. But it's still two things multiplied together. Substitution is not going to help, probably. So it's still two things multiplied together, so I'm going to do integration by parts again. So just to make it all a little easier, I'm going to do this integral separately and sub it in later. So just for me. Okay, so I'm going to redefine u and v to work with this integral. So again, if I differentiate the x, it will become a 1, and 1 times something I can deal with. So it's sort of like re-let, though that's not a word. Just my comment here is about mathematical writing. Technically, I've already used u and v, so I can't use them again. But I can just say here let, and here say redefine. And that's perfectly reasonable. Okay, so let's redefine. U is now actually x. And so u dashed is 1. V dashed is still e to the 2x. So v is a half of e to the 2x, exactly as we figured out before. And so this integral is going to be u v minus u dashed v dx. So the u is x, the v is a half of e to the 2x, the u dashed is 1, and the v is a half of e to the 2x. And now finally we have an integral that we actually know how to do. So let's see, that's half times 1 is a half, so half is being multiplied, so when I integrate it will still be there. And the e to the 2x will stay as e to the 2x, but I'll have to divide by that constant derivative. I won't put the plus c in now, I'm just going to do that at the very end of everything I want to do. So finally, I haven't actually finished the problem yet because I've figured out x e to the 2x and I wanted x squared, so I'm going to have to sub this in here. Okay, so the integral that I was actually trying to do was this one, and that came out to be equal to, can I fit them? I'm just going to bring it down. That came out to be equal to a half x squared e to the 2x minus x. So it's probably not necessary to go to this level of detail in your working, but I find it that if I do it this way, I don't get it wrong, and the person who's reading it knows exactly what I mean. So a half x squared e to the 2x minus a half of e to the 2x minus a quarter of e to the 2. Ooh, I missed an x here. An x went missing. That's actually a half of x, isn't it? Sorry about that. So I've subbed all of that in here. So this went in there. And so I've now got a half of x squared e to the 2x minus a half of x e to the 2x plus a quarter of e to the 2x plus c. So that's doing integration by parts twice. And if you're really unlucky, you might have to do it 3 times or 4, but never in an exam would they expect you to do that unless they were really nasty, and I'm fairly sure they're not that nasty. So, because you just don't have time. Right, you've only got 2 hours and you've also got probability to do, so yeah. Right, really that was the main thing I wanted to talk about. I wanted to talk about those techniques. Is there something wrong? Did I do something wrong? That's all right, because you know, if you find something wrong, you need to tell me so that everyone else can get it fixed as well. Okay. So we've got about 40 minutes, and you can ask about anything, including more stuff on integration. So ask away. Yep.
Could you maybe go through one example of, I think it's implicit differentiation?
Okay.